Hello friends, welcome to this video. So in this video, I'll be starting with unit number 2. The name of the unit is Eigenvalues and Eigenvector, and this is nothing but the portion. They are asking you to find out or learn about eigenvalues, eigenvector for a linear transformation where V is a finite dimensional real vector space. So this is nothing but our restriction. We will work on finite dimensional definitely always, but over the real only. Then eigenvalues, eigenvector for n cross n matrices, linearly independent eigenvectors, characteristic polynomial for n cross n real matrices with the finite dimensionals, vector space to itself, characteristic roots, similar matrices, relation with the change of the basis, invariance of the characteristic polynomial, and hence the eigenvalue of the similar matrices. Every square matrice is similar to the upper triangular matrices. Minimal polynomial of the matrices, example of the minimal polynomial of scalar, diagonal, and the similar matrices and invariant subspaces. So this is nothing but your portion for unit 2. I will try to cover maximum as much as I can. I'll try to complete 100%, but for now let us just start with the lecture number 1, in which I will be introducing you guys to the definition of an eigenvalue and the eigenvector for a finite dimensional vector space V. Okay, so I want to introduce what is an eigenvalue and what is an eigenvector. Okay, so what is an eigenvalue? Eigenvalue is nothing but the characteristic root. In the previous unit, we already learned what is known as a characteristic root. A root of a characteristic polynomial is called as an eigenvalue or the characteristic root. But now we will be learning that for a linear transformation. We have done it for matrices, but now we'll learn about linear transformation, and we will actually see the original definition of an eigenvalue and eigenvectors from where it is originating. Okay, so let me consider finite dimensional real vector space. Okay, so this is nothing but the short form will be used by me to write finite dimensional real vector space. Okay, I hope you guys are okay with it. So a finite dimensional real vector space V, and T from V to V is a linear transformation. LT means a linear transformation. Okay, so these are nothing but two short forms. Note first is, whenever we consider a linear transformation, it is from V to V always. Whenever we learn eigenvalues and all, we consider it to be a linear operator, means from a same vector space to a same vector space, right? From V to V always. Hence, while learning this chapter, you will note that whatever T you use, T is a linear operator. Operator. Okay, just remember this. It is not possible to have eigenvalues and eigenvector from V to W. You will see why it is not possible as such. We can define it, but it required further more knowledge. But for now, we will say that our T is always a linear operator, means it is from V to V, and my vector space V is nothing but finite dimensional real vector space. Now I will define. Okay, so a real number lambda is called eigenvalue. This means eigenvalue of T. This means eigenvalue. Okay, eigenvalue of T if there exists a non-zero vector x inside V such that my T of x is nothing but lambda time x. Okay, so I give you 1 minute to digest the definition. I will explain you now. Okay, so what I'm saying is, I have all these conditions. Now what I'm saying, a real number lambda. Okay, since we have a real vector space, so my lambda must be a real number. So my existence of an eigenvalue and eigenvector depends on my scalar field. Suppose if I have my scalar field C, then and I have a scalar field R, then both the cases will be totally different. It might be possible values are not present inside R, but they are present inside C. So you must remember, existence of an eigenvalue depends on the scalar field which you are choosing. For us, it is real numbers. Hence, I am choosing a real number lambda is called the eigenvalue of T. If there exists a non-zero vector x, this x must be a non-zero vector. I will explain you why it is non-zero, but for now let me just continue. Non-zero vector x inside V such that my T of x is equal to lambda x. So how I am finding this lambda? Okay, so definitely if you see the definition in the converse format, it become easy. Suppose if I consider a vector, let me just see in an abrupt way and a converse way. So what I will see, I have this t from v to v. What I will see is I will keep on applying t on different values. Suppose I apply it on w, I apply it on z, and after some time I'll find a vector x such that the t sending x to the scalar multiple of it means t of x is equal to lambda times x, and this x must be a non-zero vector. Then I will say this lambda is an eigenvalue. So actually the definition of an eigenvalue is actually the converse type. First of all, we get an eigenvector, then there exists an eigenvalue lambda. So we choose lambda such that there exists a non-zero vector x such that my t will send x to lambda times x. Why non-zero? Suppose I allowed the condition of 0 also, means there exists a 0 vector. Then what happen for any alpha inside R, I know that my t of 0 is always 0, correct, since linear transformation sends 0 to 0, hence it is same as alpha times 0. Means what? Alpha is also an eigenvalue now, hence since if we consider 0 as in consideration, then any real number will be an eigenvalue. So we restrict our case for a non-zero vector x. Okay, so I think this is clear. So eigenvalue is nothing but what? Eigenvalue is nothing but real number lambda such that there exists a non-zero vector such that my t will send x to lambda times x. Okay, so this x, further I will continue the definition further. I'll rub this part. Okay, further this non-zero vector x is called Eigen Vector. Okay, so I will use this for Eigen Vector. You can write it full form as Eigen Vector like this also, that is fine. Okay, so Eigenvalues and Eigenvectors. So this is nothing but the definition. So second note will be what? My question is, does this x is a unique, means for this lambda, does there exist a unique eigenvector, means there exists a unique non-zero vector such that t of x is equal to lambda times x? The answer is no. Why? Since I know that if I consider t of some alpha times x, then it is same as what? It will be same as alpha times t of x, since I consider alpha as any scalar. Now it is same as what? It is same as alpha. I know my t of x is nothing but lambda times x. I'm consider this situation. Okay, so this is same as what? This is same as lambda times alpha x, correct? If I consider alpha not equal to 0, and already we had x not equal to 0, therefore my alpha x is also not equal to 0, means t is sending a non-zero vector to lambda times that vector, right? A non-zero vector to lambda times that vector, means this is nothing but an eigen vector for the eigenvalue lambda. Hence my eigenvector is not unique, right? It is not unique. For a corresponding eigenvalue lambda, there will exist infinitely many eigenvectors. Since I know I will multiply it by any non-zero scalar, I will again get a new eigenvector. It might be possible I can get two distinct linearly independent eigenvectors also for the same eigenvalue lambda. These things we will learn in the future, but for now I think it is clear about the definition. If you have any doubt and difficulty, please write in the comment box, and please watch the previous video, and there is a quiz, guys. Please give that quiz. It is free of cost, no charges. You just have to fill the form and share it with your friend. Okay, let us just continue with this lecture. So now I'll be proving one simple result, that is a proposition. I'm going according to your portion. So let V be a finite dimensional real vector space. Again the same notation I'm using, F, D, R, V, S, P, and my T from V to V be a linear transformation. Okay, I hope you guys can read it. Okay, and my lambda is nothing but an eigenvalue of T. Then I want to prove that this set E of lambda, which is nothing but x inside V, such that my T of x is equal to lambda times x, is in subspace of V. So this is nothing but my claim. Okay, so let me just start the proof. I hope you guys have understood the statement. I will read it again. So I have finite dimensional real vector space T from V to V is a linear transformation. My lambda is nothing but an eigenvalue of T. If lambda is nothing but an eigenvalue of T, that means what? There exists a non-zero vector x such that my T of x is equal to lambda x. So this statement is trying to tell me that, right? Then I need to prove that my E of lambda, the set defined it at x element of lambda such that my T of x is equal to lambda of x. This is actually nothing but what? This is nothing but set of all eigenvectors corresponding to eigenvalue lambda. Correct? Means why I'm saying these are nothing but eigenvector corresponding to lambda, because these are nothing but collection of all those x such that my T of x will become lambda times x. Hence, every vector x is multiplied by lambda, a scalar lambda. Hence, my lambda is nothing but the eigenvalue, and all those x are nothing but the eigenvectors. Okay. So, I want to prove that for a corresponding eigenvalue, the set of all eigenvectors are nothing but a subspace of V. Okay. Now, subspace. How do you guys prove it as a subspace? First of all, I need to prove that it must be a non-empty set. Okay. So, over here, there is no restriction about a non-zero. Over here, there is no restriction about non-zero vectors, correct? Okay, so what I will do is, for 0v inside V, means a zero vector inside V, my T of 0v will be what? It will be 0v only, correct? Since linear transformations and a zero vector to a zero vector. Therefore, my T of 0v is nothing but lambda times 0v. Implies mean my 0v satisfies this condition. Hence, my 0v must be an element of E of lambda. I know that this is not an eigenvector, but still it is an element of the set. Okay. So, my 0v is an element of this. Therefore, my E of lambda is a non-empty set. Correct. Now what I'll do? I want to prove it is a vector space. So, the condition of the vector space, what I'll do? I'll consider alpha time x plus y be an element of E lambda for every alpha inside R and x comma y inside E lambda, right? So my claim is nothing but this. I will consider this and I will prove this, right? I hope you guys have remembered this. So for any alpha inside R and x comma y inside E of lambda, so it is symbol of belongs, okay, x comma y belonging to E lambda, to show that my alpha x plus y is an element of E lambda. Okay. So since my x comma y is an element of E lambda, that means what? It will satisfy this condition. Therefore, my T of x is nothing but lambda times x. My T of y is nothing but lambda times y. Correct? So I will consider what? I want to prove this, right? So I will consider my T of alpha x plus y. Since my T is a linear transformation, I can write this as same as alpha times T of x plus T of y. Correct? After that, it is same as what? It is same as alpha times my T of x is nothing but lambda times x. This is nothing but lambda times y. So I can consider this lambda common. So lambda alpha x plus y. So I got to know my T of alpha x plus y equal to map to lambda times alpha x plus y. Correct? So it is satisfying this condition. Therefore, my alpha x plus y must be an element of E lambda. Correct? Therefore, my E lambda is a subspace. Okay, I'm just leaving one line because I want to note something. So, okay, so this is nothing but a result proposition for all of you. So what we learn is my set of all eigenvector corresponding to the eigenvalue lambda with the zero vector is nothing but a subspace of V. Okay, so you guys have to think about dimension of E of lambda. What it will be? My dimension of E of lambda, since it is always a non-empty set, since 0 V is always an element of it, since it is always a non-empty set, my dimension of E lambda cannot be 0, correct? Since we know that the dimension of an empty set is 0, dimension of non-empty set must be at least 1. Hence, my dimension of E of lambda must be greater than or equal to 1. It could be 1, but it cannot be 0. Okay, so this is nothing but the note which will be used later in this chapter and also inside unit number 3 also. Okay, So this is nothing but the proposition. Just read it once, try to write it by your own. The next thing is what? Let me just see. Okay. So the next thing is nothing but the definition of an eigenvalue and an eigenvector for an n cross n matrix over R. Okay. So let me take A. Let A be an element of M of n cross n matrices over R. Again note that I am considering n cross n matrices. We never find out characteristic polynomial for non-square matrices or rectangular matrices, right? A non-square matrices we cannot have a determinant, hence we cannot talk about the eigenvalues, eigenvector and all that stuff. Also, while working on a linear transformation, we have noted we work on a linear operators, right? Linear operator from V to V only. Okay. So now let V be a M cross n matrices over R. Then I want to define eigenvalue and eigenvector. So lambda is called eigenvalue of A if there exists a non-zero. Again it is similar, right? Again there exists a non-zero x. Now it will be inside what? It will be inside Rn such that my Ax means A into x is nothing but lambda times x. Okay, so how it is? So it is nothing but, it will be A is nothing but n cross n matrices like this. My x is nothing but n cross 1. It is an element of Rn, so it is nothing but like this. It lambda times x, right? So the situation will be like this. Again the same things. This is should not be a zero vector, means all of the element cannot be zero. At least one of the element inside this column vector must be non-zero. It is similar definition, so I hope you guys can remember and understand it easily. So there is just a definition. After this there are some examples. If you have any doubt, any difficulty, and if you guys feel that I'm going fast or slow, just let me know in the comment box, so I will accordingly change the things in my next video. So now this is nothing but the proposition that I want to prove in the next video, but I will give you as an exercise or to try. So let me just read the proposition. I will definitely solve many examples based on that, but definitely in the initial or the end part of the second video. Today also we'll see one of the example, but for now let me just give this as an exercise. You can write this question. What is a proposition? Proposition stating that my V is a finite dimensional vector space and T from V to V is a linear transformation. If my V1, V2 till Vm are eigenvectors corresponding to the distinct eigenvalues lambda 1, lambda 2 till lambda m, then that eigenvectors must be linearly independent. I've given you guys a hint to prove this result by an induction. You guys can prove it, but I want to tell something about this result. What this result or this proposition trying to tell you? This result is saying that if I consider the eigenvector corresponding to the distinct eigenvalues, then those eigenvectors must be linearly independent, right? So if I consider two distinct eigenvalues and I will find out eigenvectors for them, then those eigenvectors must be linearly independent. That is nothing but this result. Result has been really important, really interesting. We'll be proving this in the next video, but for now you guys can try it by an induction. Okay, so let me just give furthermore. This is nothing but the homework questions for you. The first one, this first I will prove for you guys. I will do for you guys. Second will be an exercise, and this is nothing but from, I think it is from a unit 1. So I just want you guys to practice something from the unit 1. Okay, so homework is nothing but find eigenvalues and eigenvector for these two matrices. Definitely in the next video we'll be considering 3x3 matrices. For now I'll be working on this, and just note this down and note this down. Okay, over here you have to find out the characteristic polynomial and verify the Cayley-Hamilton theorem. So what is the Cayley-Hamilton theorem? Cayley-Hamilton theorem state that every square matrix satisfies its own characteristic polynomial. So what you guys will do is you will find out the characteristic polynomial for this matrix. So it will be a polynomial of degree 3. What you will do, you will find out a cube, a square, a and I. You will substitute these values inside the characteristic polynomial of a, and you will prove the answer is coming out to be a zero matrix. Okay, this is nothing but the task for the second one. Okay, so let me just work on this. I will find an eigenvalues and eigenvectors for the first one. Okay, so definitely I have already done the simple part. I have this matrix A is nothing but 1, 4, 2, 3. The determinant of this is nothing but 3 minus 8, that is minus 5. characteristic polynomial by the trick video that I have given you. That trick gives us direct answer. So it is lambda square minus tres. Tres is nothing but 1 plus 3, so I wrote 4 times lambda, plus nothing but the determinant, which is minus 5. Since I wanted characteristic polynomial, I should have written this much only, not equal to 0. Now over here it becomes a characteristic equation, correct, because it has an equation. So it is nothing but the characteristic equation is this. So what I did, I just split it. So it is lambda minus 5, lambda plus 5 equal to 0, so lambda equal to 5, and lambda equal to minus 1 are nothing but my eigen values, right? Eigenvalues for this matrix. Okay. Now I want to find out then eigenvectors. What are the eigenvectors? Eigenvectors are nothing but a non-zero vectors which will get multiplied by 5 after applying this linear operator or by applying this matrix. So let me just find out. Okay, so what I will consider is ax is equal to 5 times x. So my a is nothing but what? A is nothing but 1, 4, 2, 3. I will write it as xy is nothing but 5x, 5y. Okay, so after opening this or multiplying this two, I'll get x plus 4y, 2x plus 3y is equal to 5x, 5y. Okay, now what I will do, I'll just equate it coordinate wise or the element wise, entry wise, right? So I will get x plus 4y is equal to 5x. That means nothing but this will go other side, so it becomes 4y is equal to 4x. So my x must be same as y. Let me just consider the second equation also. The second equation is what? So second equation is nothing but 2x plus 3y is equal to 5y. So again this will go to other side, so I get 2x is equal to 3y, 5y minus 3y is again 2y, so my x is equal to 1. So from the both I am getting the same equation. So my x is nothing but x comma y. So x is nothing but, I know x is same as y in the both the cases, I am getting the same. So it is nothing but what? X comma x. So my x is nothing but x of 1 comma 1. So I got x is nothing but any vector which is multiple of this 1 comma 1. So my e of lambda is nothing but what? E of lambda, or I will write e of phi, that will be more precise, right? So my eigenspace for eigenvalue phi for this matrix A is nothing but alpha times 1 comma 1, where my alpha is any real number, correct? Also you will see this 1 comma 1 is nothing but my eigenvector, since it will satisfy this condition. Also any multiple of it, because I have no restriction on x, right? I can choose x as any number, so I will consider it to be any real number alpha. So anything like this where alpha is any real number will be nothing but my eigenvector. For alpha not equal to 0, it will be an eigenvector, right? So these are nothing but my elements of this e of lambda. Okay. Similarly we will find out for minus 1 also. So again the same thing, I will consider ax is equal to minus of x. A is the thing but what? It was 1, 4, 2, 3. So it was 1, 4, okay, sorry, 1, 4, 2, 3. It is xy minus x minus y. Let me just simplify. So again the similarly, so it is x plus 4y, 2x plus 3y is equal to minus x minus y. So equating again we'll get x plus 4y is equal to minus x, 2x plus 3y is equal to minus y. From this I will get what? I'll get this will go to other side, so I get 4y is equal to minus 2x. So my 2y is equal to minus of x. From this I will get, this goes to other side, so I will get 2x is equal to minus 4y. So x is equal to minus 2y. So from the both I am getting the same equation. So my x was what? My x was x comma y, that is nothing but this, but will become what? It will become minus 2y y. So it is same as what? It is y of minus 2 comma 1. So my eigenspace for this minus 1 is nothing but alpha times minus 2 comma 1, where alpha is nothing but any real number. This is nothing but an eigenvector, or any multiple of it, any non-zero multiple of it is nothing but your eigenvector. Okay, so you guys will prove that this vector 1 comma 1 n minus 2 comma 1 is linearly independent. Okay, so if you prove this, you will understand this result. Since you know that my 5n minus 1 are nothing but distinct eigenvalue for this, the corresponding eigenvector must be linearly independent. For the 5, I know one of the eigenvector is this, and any non-zero multiple of it is also eigenvector, but I know this is nothing but one of the eigenvector, 1 comma 1. For the minus 1, the another distinct eigenvalue for the same matrices has an eigenvector as minus 2 comma 1. So you will prove that these two vectors are nothing but linearly independent. So you are verifying that result. In the next video we'll see more example. Please guys, try to do those homework questions, and if you have any doubt, any difficulty, please write in the comment box. Please share, subscribe and share your reviews in the comment box. Okay, thank you guys, bye bye.